So this is interesting. Woo. Today, we're going to try and measure the speed of electricity using this 1980s Hitachi V212 analog oscilloscope. Specifically, we're going to try and measure the speed of an electrical signal through Cat6 Ethernet cable. This video was very much inspired and influenced by similar experiments done by AlphaPhoenix and ElectroBOOM, and I've linked their videos in the description down below, which you should definitely check out. And when you come back, I think this video will still be worth watching because I'm going to bring up some questions and critiques that I have based on their methods, and I hope that if others have answers or other perspectives, that they would share it in the comments below. And also, we're going to be doing our measurement on this beautiful piece of equipment right here. Now, an analog oscilloscope is not going to be as versatile and feature-rich as a digital oscilloscope, but there's something, to me at least, that's really beautiful about the way that the analog oscilloscope is going to present the data to us. And I don't know, something about that electron beam sweeping out the signal on the phosphorescent screen that makes it seem more real in a way that a digital scope sometimes kind of strikes me as just, I don't know, I'm looking at a simulation on a computer screen. So I think it'll be a lot of fun to use this piece of technology here. In order to get a better understanding of how electricity will flow through our wires and through our components, I made a little diagram here for us to look at. Now, the gray square at the bottom is meant to represent the battery, and the circle at the top is supposed to be some sort of resistive run light bulb. So think of your typical incandescent light bulb. And the black lines are the wires connecting them, and I've put just some representative electrons as these yellow circles with E's in them. Now, obviously, there are way more electrons than I can draw on the screen, and only some of the electrons in the conductor can move. Most of them are going to be still bound to their nuclei in their respective atoms, but it's these free-flowing electrons that will carry the electrical signal. Now, the battery can do something sort of special. It has chemistry inside of it, if it's like a typical alkaline battery, which are the type that we'll use, which will allow on the negative terminal here for this electron to get captured, and some sort of chemical reaction will happen, and so that electron will be taken out of the wire, and a new electron will be deposited on this positive or the negative terminal of the battery here. And the electrons will repel each other via the Coulomb force, and that will cause this sort of compression wave to move through the wire. And it's really this compression wave that represents the electrical signal, not the individual electrons making it all the way around the wire, because the electrons actually move fairly slowly in wires. It's called the electron drift velocity, and it's fairly low, whereas the compression waves will move much faster, and as we'll see, it's going to be about equal to the speed of light in that medium. So if we imagine that the electron sort of the battery did this sort of magic here where a chemical reaction allowed it to take an electron off of the wire here and put an electron here, let's see what happens when the electrons repel each other here, and also on this side there's sort of a gap where there's not a force holding these electrons back. And so we get this compression wave that moves out to the right, but on the left you can see there's sort of this rare refraction, and then when they make it to the light bulb, it's these electrons moving much more slowly through this resistive wire that creates heat, and if the heat is hot enough, we can see it as visible light. So let's look at that process again. So we have this compression wave moving out to the right, and at the same time we have this sort of rare refraction electron gap moving at the same speed to the left. And that's sort of how I think about electricity flowing through a wire. And importantly, the electricity flows out from both ends of the battery, and they here are meeting in the middle where there's a light bulb. But if you imagine that the light bulb were in the bottom left here, for instance, it would light as soon as there's any part of this compression or rarefaction wave moving through it. So that light bulb would light down here if it were located close to the battery. So I think that this is an important thing to think about, because in AlphaPhoenix's video, he gets rid of this half of the loop and has the resistor just down here. And I'm not clear as to why there's still a significant delay, because it's not the case that the electricity has to travel all the way out where the electrons are compressed down to the battery on this side. They go out in both directions. And actually, in an earlier video of AlphaPhoenix's, where he does this experiment where he has the resistor in the middle of a long loop of wire, which I'll also link in the description, he does show these electrical waves traveling out both ends of the battery. And so it's not clear to me how his experiment works the second time when he gets rid of that one half of the loop. I wanted to take a look at AlphaPhoenix's and next ElectroBOOM's videos, and specifically the parts where they're describing why they only need the one loop of wire and still getting the time delay for the light bulb to turn on in their circuits. And I still disagree with this view of the way that electricity is flowing based off the model that we just looked at. So let's listen to what they have to say here.
In the previous video, I had a loop going out from the battery and switch in both directions, and then approaching the resistor or the light bulb that was the load. And one of those loops really didn't matter, so I've removed it.
So in this model that he shows, where he says that you just need the one loop, I still think that from the positive terminal of the battery, you have an electrical signal being sent out as the sort of whole of electrons at the same speed. So it should reach the light bulb in this circuit pretty much immediately, even if this length of wire here is very long. And then he also has this diagram where he's showing the flow of electricity, which let's take a look at it.
When we flip the switch, all of a sudden we dump a bunch of electrons into one end of the wire. These electrons want to spread out and make the whole wire neutral again, but they don't spread out like this, they spread out like this, where each electron just moves a tiny bit until they're all evenly spaced again.
So that view of what's happening at the negative terminal of the battery, I completely agree with. However, it's not just that the battery pumps a bunch of electrons on this terminal, but it should be taking away electrons out of the wire on the positive end of the terminal. And so you should have that same sort of motion, but on the other side of the wire as well. And what's interesting is that in his original video where he had that full loop of wire, he does show the electricity flowing out of the battery in both directions. And so I'm not really sure how he was able to get this just one loop of circuit to work with the time delay with the resistor near the positive terminal of the battery. And so ElectroBOOM seems to do the same thing with his circuit.
Is if in the original setup it would take, say, 1 second for the electricity to travel through 2 loops to get to the load, now it still takes 1 second, but through 1 loop. The load...
So here again, I think that the electricity will flow from both sides. So if you have this really long loop where it takes 1 second for the electricity to make it to the light bulb, well, if it takes nanoseconds for it to reach the light bulb from this end, then, or even less, picoseconds, then it should just take picoseconds for the light bulb to turn on. Now, ElectroBOOM ends up using a slightly different model for his measurement, where he's looking at this reflected wave at the end of the transmission line. So that's why his calculation still makes sense to me, but his explanation for why the light bulb turns on instantly, I disagree with. It's because it's connected very closely to the battery, not at the end of the transmission line, and he's just looking for that step which we'll explore in a moment why that is happening. So for our experiment, we're not going to be directly measuring when just any electricity flows through a resistor. Instead, we're going to model our Ethernet cable as a transmission line because it is a type of transmission line, and that also allows us to get a lot more wire where we don't have to have a single strand of wire that is spaced far enough apart that it's not capacitively coupled with like the ground or any other wires like AlphaPhoenix had to. So this arrangement is the way that ElectroBOOM did his measurement. And so we have a battery hooked up to a resistor in series with that battery, and then a transmission line with some impedance Z0, and then there could be some resistance here at the other end of the transmission line. And we'll look at how to calculate the voltage across this resistor, or really at any point along the transmission line in this sort of a setup. So the way to do these calculations is using something called a bounce diagram, where we have the battery at a distance 0, or I guess the start of the transmission line, and then it has some length L, and so what's the voltage at some point X in the horizontal axis here, and then time is increasing as we move upward. Now, as these signals travel through the transmission line, they will bounce on both ends, in that, or they'll reflect. And that coefficient of reflection on the source side is given by this gamma Vs, which is the resistance of that source resistor minus the impedance of the transmission line over Rs plus C0. And then there's also a reflection coefficient at the end of the transmission line, which is the same but with that RL instead of Rs. So in general, we have that there is some outgoing voltage, electromagnetic wave traveling down the transmission line, and the voltage will be given by this ratio of the impedance to that Rs times the voltage source, or this voltage of our source, our battery, and then it reflects. So you have this coefficient of reflection times the V1 plus, and you get this reflected V1 minus, and then you get a V2 plus in the other direction, where the coefficient of reflection is now given by that at the source, and then it also bounces back. And this can happen ongoing continuously until you reach a steady state. So just to give some specific examples, if we happen to have a Vs of 40 volts, an Rs of 150 ohms, an impedance of 50 ohms of the transmission line, and that RL is 16.7 ohms, when you plug in all those numbers, you get these values for the coefficients of reflection. And so this original signal will have 10 volts, and when it reflects, you'll get negative 5 volts. And then when it reflects again back at the source, you'll get negative 2.5 volts, and so on. And so this would be what a plot at, they're imagining here a 100 meter transmission line. So halfway, 50 meters, you're going to get the 10 volts. And then based off the properties of the transmission line here from this Introduction to Physical Electronics textbook talking about bounce diagrams, they just have the transmission line have the properties where these are the time calculations, and we can see the voltage as it changes over time. Now for our diagram, we have a source voltage of 3.3 volts. We are going to say or put a resistor of 100 ohms, and the Ethernet cable should have an impedance of 100 ohms, and we're shorting it, so their RL is 0 ohms. When you plug in the numbers here, you would see that the coefficient of reflection at the source will be 0, and the coefficient of reflection at the end of the transmission line will be -1. So when we do the calculations, we'll get half of the voltage immediately in the transmission line of 1.65 volts, and then it will travel all the way down, and at 1 amount of time for the signal to travel to the end of the transmission line, it will then bounce back and have a voltage of negative 1.65, which will then exactly cancel, and you have this coefficient of reflection of 0, and so users have 0 volts. So in LT-Spice, I've made this diagram here, this circuit that should represent what we're going to set up and measure on the oscilloscope. So we have this voltage source that will send out pulses. Now this is just telling us that the initial voltage is going to be 0 and go up to 3.3. Tried to put some reasonable values of the rise and fall time, 50 nanoseconds. Just pulling numbers out of my hat, out of a hat here to be reasonable, but I didn't get too precise. And then the period for the 400 kilohertz signal, and 1.75 is the time that it's on because it's the 50% duty cycle. So I'm also at first here going to have 0 internal resistance of our voltage source, which we know isn't true, and we're modeling this as a lossless transmission line with the 400 nanoseconds should be roughly the time for the signal to travel down the transmission line. But of course, this is what we're going to be measuring, and an impedance of 100 ohms. So if we go ahead and we run the simulation, and we take where our oscilloscope is going to be taking a measurement here, and so we can see we get these pulses of 3.3 volts. Oh, I messed up my... This shouldn't be 1.75. This should be 1.25. Okay, and now we're getting the 50% duty cycle. And so we can see these voltage spikes up to 3.3, and then they fall back down to 0. And then we'll measure it just after the resistor. And we'll see that the resistor will go up to half the voltage, that 3.3 divided by 2 is 1.625, I think. And then after the time for the signal to go all the way down the transmission line where it's shorted and all the way back, then it will fall to 0 if the impedance matching is perfect. Now, if we change this a little bit to add some series resistance, let's just start with something small just to see what happens. So let's say 10 ohms. You can see that the signal will be a little messy, right? Like the voltage at the source won't be exactly constant. It'll be affected by that. And we'll just get a little bit less clean of a signal. Let's try boosting this up to 50. Okay, and so now the signal is even a little bit messier. But the important part is that the width of this bump here should still represent the time for the signal to travel down the transmission line and back. So that's really the signal we're going to be looking for, and we might expect to see the voltage levels here to not be exactly constant because there will be some output impedance of our Raspberry Pi Pico signal that we're going to use to measure the speed of electricity in this transmission line.
Okay, now that we have an understanding of how electrical signals pass through a conductor, let's take a look at the specific experiment that we have set up here. So the first thing that we want to do is take a look at how we're going to turn on and off this signal through the oscilloscope. Now we're going to use a square wave generator instead of hitting a manual switch or button. As AlphaPhoenix discussed in his video, you get a lot of bouncing where the switch contacts that close won't make an immediate permanent connection. They'll kind of bounce a little, and so our signal will be a little noisy. So instead we want to do this electrically. Now I just have a Raspberry Pi Pico here set up. All it's doing right now is running some simple code, which I have displayed on the screen now, in order to produce a 400 kilohertz
PWM signal at 50% duty cycle. So this should give us a square wave, and I've got the scope hooked up to the PWM output there. So if we take a look at the oscilloscope here, let's see when we switch it from ground to DC, and increase the intensity, we focus it a little bit better. We can see the signal here. So it's flat, and then it has these very distinct jumps to this higher voltage. And if we look at our voltage division of 1 volt and count up the divisions on the screen, you can see it's about the 3.3 volts as we expect. And I have calibrated the oscilloscope to match that amount. Now, before we run this through the Ethernet cable, which will act as a transmission line, we want to be able to match the impedance of that Ethernet cable. This will give us the clearest signal to noise when we measure the voltage across the resistor at the end of the, that will change as a result of that reflected wave at the end of the transmission line. Now, in order to do that, we need to match the impedance of the Ethernet cable. Now, luckily, that information, the impedance of the Ethernet cable, is widely available, so we know it's and tested, and we know that it should be 100 ohms. So we want to try and match that. However, as ElectroBOOM discussed in his video, the output of this signal, our signal generator, has some output impedance that will interfere with that. Ideally, we want it to have 0 output impedance. Now, for this Raspberry Pi Pico, I wasn't able to find what the output impedance is, so I thought it would be a good demonstration to show how we might calculate that value. So what we're going to do is we are going to pass the signal through some resistors of known values, known resistance, and from that we can calculate the output impedance, because the change in the voltage of our signal that we get will depend on both the resistance of the resistor as well as the output impedance of the signal. So if we know the resistance that we're adding to it, we can calculate that unknown of the signal's output impedance. So because I'm going to be connecting this to ground, the signal directly to ground, we want to make sure there's some resistance that goes into it. If the output impedance happens to be very low, then maybe we'll be drawing too much current from the Raspberry Pi Pico. So we'll start with a large impedance. So this is a 1 kilo ohm resistor that I am just going to put the output of our signal generation into this resistor. And then I'm going to connect the resistor to ground. Now, the way that the Raspberry Pi is set up is simply that I am using 3 AA batteries to power the Raspberry Pi, and it's really just power going to the system of the Raspberry Pi, and the ground here going to ground. And the only addition to that circuit is that just to protect the Raspberry Pi of any, reverse current flow, there I have a diode. So the positive of the battery runs through a diode before it runs through the power of the Raspberry Pi Pico. And now I'm taking the output signal, which I have on pin 15, and passing it through a 1000 kilo ohm resistor. And as I connect it to ground here, if we pay attention to the screen, we should see the voltage drop. If I did this correctly, which I did not. Okay, we should see the voltage drop. Okay, it's a very slight drop. So it's pretty hard to see the drop in the voltage, but it's maybe 1 tick mark, and there are 5 tick marks per division. So if it's at 1 volt per division, that's 0.2 volts. So that's pretty small. So we don't have to use such a high resistance resistor. What we're looking for is when we've exactly matched the impedance of the Raspberry Pi, is that it will drop in voltage by half. Now we don't have to get it at exactly that to do the measurement, but it will help the calculation, the precision of it, to be able to have a larger drop in voltage. So now I'm going to use a 100 ohm resistor and perform the same experiment. Okay, so now we're looking at a drop from the 3.3 volts right here. Okay, so this is a much clearer signal. Oops. So we can see that instead of going to 3.3, it's now maybe going to 1, 2, and then maybe 1 tick mark, so that'd be like 2.2 volts. Okay, so in order to measure the output impedance, we are going to use the formula that the impedance is equal to the difference between the two voltages, so 3.3 minus 2.2 times the resistance of 100 ohms divided by that second output voltage that we read. And so we get almost exactly 50 ohm impedance, which is pretty reasonable since that's a fairly common output impedance value that you'll see with function generators and power supplies and whatnot. So that seems reasonable to me. Now, that value might be a little high and interfere with our 100 ohm impedance transmission line. So what ElectroBOOM does in his video is he uses a circuit which will allow him to use the function generation in order to create a new signal that has a very low impedance. And to do so, the circuit that he uses, which you can see here, involves putting three PNP transistors in parallel, and then just as he shows it, running the signal generator directly to the base of these transistors, and then using a different power source, which is why I'm using the battery for the Raspberry Pi instead of a USB, so I can tap into these batteries as running from the transistors between the collector and the emitter. And he also includes a 100 ohm resistor going to ground. Now, my understanding of the need for this 100 ohm resistor is that the three transistors won't all be exactly the same in their specs. And so if they're just a little bit different, then it will cause certain issues where much more current is flowing through one transistor than another. And so there's something about using the resistor to connect to ground that sort of helps smooth all of that out and lets them act or behave kind of more cleanly in parallel. And so then we'll just take the output from before that resistor goes to ground. Now, when I have tried this, however, I did not get the result that ElectroBOOM got. So I'm going to take the signal of our function generator and run it into the base of these transistors. And then I'm going to use power from the batteries before it goes into the Raspberry Pi, because the sort of in series internal resistance of the batteries is very low, so it can give us a very low output impedance. So I'm going to take that signal and put it into our transistors. And so then when I hook this up to ground, we should get the low impedance signal here. Now, one thing that's interesting to note is that we're already getting something weird on the original channel of the oscilloscope. So it already seems like something sort of funky happened, and it's not clear what that thing is. Right, and it doesn't seem to be a setting on the oscilloscope. Let me get my second probe. And so now we're going to probe the output of the transistors. Maybe it messed up the original signal somehow, but these still work. I don't think that's happened because now we just have a positive voltage going to the base of these transistors, so it seems like they're probably just on. Let me hook this to ground. Yep, so we still just sort of see it seems to be always at this higher voltage. And so now when we measure on the second channel of the oscilloscope the output from this transistor, I have this ground here, and go to channel 2. So again, we just see some positive voltage here. So I'm not really sure how ElectroBOOM got this to work. To be fair, he was driving an LED, which is a diode, so maybe there's something about the direction of current that was running through there. But so far as I can tell, and I tried it with a diode, that doesn't seem to work either. So I'm confused about how his circuit worked. If anyone has an understanding of what's going on, please comment below. As best as I can tell, I think it's because the output voltage of the Raspberry Pi is that it's running at is the signal is at 3.3 volts, whereas our 3 batteries are obviously at roughly 4.5 volts. And so I think that the current is able to run from through the resistors, through the base in the, oh gosh, I'm gonna get this backwards, through the emitter. I always with the PNP and the NPN transistors being backwards, but where the positive voltage is applied to the PNP transistor flowing through the base back to the Raspberry Pi, which you wouldn't normally expect to happen. That's not like the regular way in which the transistors are supposed to be working, to be acting as a switch here. But I think that that little bit of current flow essentially means that the transistor is always on. And so that's why we're just having it constantly be on here. Maybe if the voltage that we were running in order to get our low output impedance signal were lower than the voltage of the Raspberry Pi, this wouldn't happen. But if you look in ElectroBOOM's video.
Hey, teacher Brian here. I'm not sure why in this part I mixed up my words so much, but basically what I'm trying to say is if you look at ElectroBOOM's video, his function generator, as he displays on his oscilloscope, is clearly under 5 volts. This is 5.35 to 4.35 between these divisions, and the signal is below the midpoint. And the midpoint here will be under 5 volts. And so it's clearly under 5 volts. Whereas if you look at the schematic that we looked at before, he's driving this driver circuit at 5 volts. So his setup is similar to mine in the sense that the driver circuit has a higher voltage than what the function generator is creating. And so I think that he would get this curve this trace that doesn't have the square wave signal in it anymore. So I'm confused about how he got this driver circuit to work.
Now, in AlphaPhoenix's video, he doesn't share what his circuit is, so I'm not actually sure how he is running his signal, and we can't test that. But we also, again, are unsure on why he's getting a delay time when it seems like the resistor is hooked up very near to the battery. And he's not depending on, right, this reflection like in ElectroBOOM's video, which is why the calculation works for him. So instead what we're going to do is we are going to just try and use this higher output impedance signal from the Raspberry Pi and hope that it is good enough, I guess. So I'm not going to unwind the Ethernet cable, and obviously we have the twisted pairs inside. ElectroBOOM goes into some good detail in his video as to why this shouldn't really affect our measurement, but Essentially, it's just because this is acting as a transmission line whose understanding and calculations have built in that capacitive coupling and whatnot. And so we're just essentially wrapping that into the known impedance of the line. And so it shouldn't affect the delay that we measure in the resistance. Now I could have cut this open like ElectroBOOM did, and you could see the wires and I could just short them, but I didn't feel like doing that. And so I have these breakout circuits where we're doing the same thing ElectroBOOM did. Now, what that means is we're not going to use the 100 feet of length that's here. We'll effectively have a transmission line that's 400 feet because there are 4 twisted pairs. And so the signal is running through one twisted pair and then connected to another on the way back, and then connected to another on the way down, and then another on the way back. And so you're getting what is effectively the equivalent of one twisted pair that's 400 feet long. So this should be helpful in getting us the resolution that we need on the time scale, because this is only a 20 megahertz oscilloscope, so we don't have as much precision in the time domain. Now, let's get our scope hooked up across our 100 ohm resistor to do the impedance matching, and we're just going to, for the moment, ignore the output impedance of the Raspberry Pi and just hope that this will be good enough. So we're taking the signal from the Raspberry Pi, putting it through the resistor, and then hooking that up to the transmission line, and we're going to hook this up to ground. Okay. Now we are measuring on one side of the resistor the signal, and on channel 2 we are going to measure on the other side of the resistor. So effectively we're measuring the voltage drop across the resistor. This up to the common ground. Okay, I'll switch to channel 2. I haven't looked at this yet. Okay, so we're also getting step function, which is to be expected. And now let's look at both at the same time. On the same scale. Well, that didn't give us the result that we expected. Okay, I've looked at the model that I made in LT Spice of this setup, and I realized that I had the time delay for the transmission line incorrect, because I was thinking that the transmission line was roughly 400 feet and light travels at roughly 1 foot per nanosecond, so I had 400 as the value here, but I realized that that's the speed of light in a vacuum, and it will be slower in our transmission line, and we'll talk about that at the end of the video. But because of that, this delay is more like 700 nanoseconds. So when I run the same analysis here, I still have my pulses from the function generator, but after the resistor, the pulse turns off before there's been enough time for the signal to make it all the way down to the end of the transmission line and back. So we actually are getting the same sort of result that we measured on the oscilloscope. And so if we slow down our pulses, so maybe instead of the total period being 2.5 microseconds, if we change that to be, oh gosh, well, let's just say 4 microseconds. and so then it's on for 2 microseconds. Or no, let's do more. Let's say it's on for 5 and 2.5. Then we can see that there is time for the signal to get all the way back, because it's going to take maybe roughly 1.4 microseconds, right? So twice this time. I mean, I don't know if it's going to be exactly 700, maybe more like, you know, in the 600s or something, but we just need to have a slow enough pulse in order to give that wave of the electromagnetic field time to propagate and reflect back at the end of the transmission line. And so now this is the curve that we will expect to get the trace on the oscilloscope. So let's make that change and see if we get the correct result now where we can get a measurement. Okay, so now that we've done the correct math to determine what frequency of square wave we should use, we've come back and we've changed the Raspberry Pi to have that 100 kilohertz frequency. And so now there will be enough time for the signal to propagate all the way down the Ethernet cable and all the way back to the resistor. So I've got this set up on the oscilloscope the same way that it was before with the same time step, but now if we look at channel 1, instead of going from 1 division or 0.2 microseconds per division, if we switch to 1, or did I say hertz? Microseconds. 1 microsecond per division, we see we've got now this much longer pulse. Now, it doesn't have to be, in theory, a repetitive signal. Once we turn the switch on, we just want to measure it once when it's on. But this is one of the features that a digital oscilloscope will have, in that it can run in single mode, where you can have it, once the trigger gets hit, it will collect data for as many samples as it can take, and then it will stop. With the analog oscilloscope, we can't do that. We have to have the continuous signal going on and off, and so that way we can look at then that moment in time that's getting repeated over and over and over again. We can't just look at it once and freeze the screen, unless maybe you had like a really fast camera and knew exactly when to like hit the shutter to take the picture. So we're looking at channel 1, where we're measuring the Raspberry Pi Pico signal here. And so now we're going to look at the resistance on the other side, or sorry, the voltage on the other side of that resistor. And so by switching to channel 2, and so now we can see that it has this plateau here where it goes to like half the voltage, and then we actually see it falling back down, not all the way to 0, but that is because there is the output impedance of the Raspberry Pi. So once it reaches that steady state mode, the impedance of the Ethernet cable is effectively not there, because it's not really an AC circuit on this plateau here. And that 100 ohm impedance will sort of go away, and it will just act as a wire connecting the DC voltage. So we would normally have all of that voltage get dissipated across that 100 ohm resistor, but because we also have the 50 ohms of output impedance from the Raspberry Pi, some of the voltage is sort of getting lost there. So it's not going all the way down to 0. At least that's my understanding. If I'm wrong about that, please let me know. So now if we look at both of these together, we can see that the Raspberry Pi sends the pulse, and then during, and the resistor, because it is right next to that power source, we also see the voltage on the other side go up as well, because as we saw in that diagram, the wave of electricity goes out in both directions, not just one direction from the battery. So that goes up immediately, and then there's this time. It's not perfectly flat, this setup isn't perfect, but relatively flat, and then it drops. So that's the delay time for the signal to travel all the way down the transmission line, this Ethernet cable, to reflect and go all the way back. So that that 400 feet down, but importantly then the 400 feet back. And then, so then it settles at that larger difference there. So at first, some of the voltage, because the difference between these two curves is the voltage being the voltage drop across the resistor. So some of that is happening in the impedance in the transmission line, but then once it establishes that DC curve, and we don't have a lot of bouncing because I guess we're pretty close to matching the impedance, then you have a larger voltage drop across the resistor. And we can also look at this, interestingly, by adding these two curves and then inverting the second one. So we see at first there's no voltage drop across the resistor, and then when it goes on, there's some voltage drop across the resistor, and then it jumps up again to this higher voltage drop. But it's just a little bit harder maybe to analyze our circuit there. So now we want to measure the width here on this second channel. So we have it set up for the divisions to be 1 microsecond per division. And so now to make this a little bit easier, I'm going to bring this curve down to the middle here, where it's still in line. I had moved the time so that this spike happened on a division. And then if I move this second one down, it's sort of easier to see now where that fall happens. And it seems to fall at exactly 1 tick mark past 1 full division. Each tick mark is a fifth. So that makes it 1.2 microseconds. Now, there is some additional length of wire, obviously in these jumper cables, but I think we're just going to simplify it and say that we're looking at this time for the signal to have traveled 800 feet. So if we do our calculation now of 800 feet, we want to convert that to meters. That 800 feet is 243.84 meters is our distance. And our time, we said, was 1.2 microseconds. It's e to the negative 6. Oops. Oh, forgot an equal sign. And so now our speed is just d over t. So we're getting 203.2 million meters per second. Yep, and so that is roughly, we'll just say 200. That's roughly 2/3 of the speed of light in a vacuum. Now, the reason why that this is not equal to the speed of light is because the speed of light in the conductor is not going to be equal to the speed of light in a vacuum. Now, when AlphaPhoenix does this calculation, he gets values extremely close to the speed of light in a vacuum. And my understanding of that is because the electrical permissivity of copper, which is the wire that he uses, is very close to 1, whereas in this Ethernet cable, it's aluminum, and that value is significantly different than 1. And permissivity is part of the calculation of the propagation rate of the electromagnetic waves in the whatever medium you're talking about. So there we have it, the speed of electricity in this Cat6 Ethernet cable, or perhaps more generally, the speed of electricity, which is equal to the speed of light in aluminum. So I think that this was sort of a fun experiment for me to do. I hope you all enjoyed it. We brought up some interesting questions compared to AlphaPhoenix and ElectroBOOM's videos that I hope that there's some discussion about. So how is ElectroBOOM's, how is his transistor circuit working? Also, what would be the correct transistor circuit to work there? Is it a coupled pair of transistors? Is it a Darlington pair? These are other circuits that I didn't try out, but maybe in the future could, or if people had recommendations. In terms of ElectroBOOM's analysis of why that light turned on immediately, I think that that's incorrect, that it is not that electric field propagating from the switch. I mean, that can have an effect, but it will be very small. It won't be half of the voltage of the battery. It's simply because the light on the other end of the battery is right next to it. And his sort of analysis that the wave has to go all the way down the transmission line and come back in that one direction is not correct. It's that the waves travel in both directions and then bounce and come back. And it's that back on both wires at both ends of that loop, or sides, I should say, that then affect the voltage across the resistor. And in terms of AlphaPhoenix's video, it would just be interesting to know how he set up his circuit in order to measure that delay, even though the resistor wasn't in the middle of the transmission line. And as one last sort of fun thing that I thought we could do is we could see what happens when we make this an open circuit, in order to see that we should still have this initial blip here, but then it should go to no voltage drop across the resistor, so that voltage should go up to the line where we're measuring the output signal from the Raspberry Pi. So if I set this up correctly, we should be able to just disconnect this wire here. Oh, okay, so that did sort of greatly affect the, because of the output impedance of the Raspberry Pi, that kind of top voltage level. But I think it's interesting that you see this first little blip there looks the same and it's roughly at the same distance. So let's see if we can like connect and disconnect to sort of see where the first part of that circuit is the same. So yeah, it's kind of a cool little double check on that this setup worked correctly. Well, thanks so much for watching, and I hope to see you next time.